I'm Jesper Dramsch, and I'm currently doing a PhD at the intersection of machine learning and geophysics, and I would like to crack open the black box. If you'd like to read more about it, go to my blog at the-geophysicist.com. But now we're going to make sense of machine learning and neural networks. Let's start with some motivation from other fields. So one of the biggest is probably self-driving cars. I mean, no one would have imagined this just a decade ago. And now you have a camera on a car, you see them driving around in San Francisco, and on the right you can see how they actually see. So you have this machine learning model in your self-driving car that knows to distinguish between cars, between bikes, between humans, and the road it's actually supposed to be on. If you want to have a further look, I have all the sources on the presentation, so you can actually just pause the presentation and Google in another window to have a look what this is actually about. Another really cool image is from remote sensing. This is image-to-image translation with something we call generative adversarial networks, or short GANs. And this is from satellite images to maps. We can map from black and white colored images to actually colored images, and they look really realistic. Definitely look up that nice paper that I put there. It's fantastic. You can even, and this is more esoteric, more obscure, map from a day scene to a night scene, or from a sketch that you have to realistic images like this handbag sketch that gets turned into a handbag. And now a bit less detailed, but broad stroke, we have drug discovery where you use GANs. They try to find biotoxicity in new molecules that both get generated by GANs. We have Sören working with GANs. Those are the people in Switzerland that just found the Higgs boson. We have the board game Go. So Lee Sedol was just beat by the DeepMind algorithm AlphaGo, and no one thought that would be possible because the search space for this game is so large that no one thought this would be happening anytime soon. Then computer games. I mean, we always play against computers, but this game, Dota 2, is so complicated that everyone was sure this wouldn't work. And this recently, just April 2019, beat the top performers in that game. And don't knock the game, because tournaments in this game are doted at $1 million and higher in prize money. So this is a real achievement. Bit more esoteric and kind of cute. They train your dragon. So it learns to fly this path from a state where it actually doesn't know to fly. Maybe you can see how to use this in drones, for example. And something that I personally find very important and very interesting, this is cassava. Cassava is the third most important source for carbohydrates in the world. Basically, the entire sub-Saharan African countries rely on this for food, but there's several diseases that threaten food stability, and people have built an app for your smartphone. Just snap a picture and you can identify if it has plant diseases. All of this just with machine learning models. So there is so much happening. What can we do? So I want to talk about what is machine learning, how do we do machine learning, and how do we make sense of the models? Because those are the three essential parts that you have to know to actually build your machine learning models. Classical algorithms work in a way that you have your data and your rules, and then you get out your answers. Now, machine learning algorithms turn the entire thing around. You have your data and you know your answers, and you get out rules. You can think of this, for example, in well logs and network rows. So usually you have your well logs and you have your log interpretation, so you know the rules that you want, and you get out your network rows. Now, what we do in machine learning is we get, for example, an interpretation from core and mix that with our data, so we know the data and the answers, and get a model that hopefully can generalize to other worlds. So tell us on other worlds how the net to gross is doing. Algorithm is a bit of a wonky word, right? Like, what is it actually? Well, I want to give you some names. I'm just gonna name drop them, and you can pause anytime and just have a look what this is, or maybe use this in other courses that are available on the internet, sometimes for free. Just check it out. So neural networks are a good place to start. Those are the ones that kind of sparked the boom that we have right now. Random forests are extremely powerful classifiers as well. Then for clustering, we have HDB scan and k-nearest neighbors, and support vector machines are also a really good model to know. And since you're watching this in the future, there's going to be many more. Going from machine learning to deep learning, we're focusing on neural networks. Neural networks take an input, and all these arrows, you can basically think of them as a number that you multiply your input with, and then in the circles, we call them neurons, you just sum them up and apply a function to them. And these have been known for decades. So a very long time ago, people came up with this concept of a neuron, then they started neural networks. And now, by adding more layers, you can see that the combinations that we have in this entire thing are really, really powerful. And this is what deep learning is. You have deep neural networks with several layers. So you can see that your input well and your net to gross get matched by these huge combinations of functions that are applied to it, usually nonlinear functions. Have a bit of a look at names in neural networks as well. Once again, you can pause this and have a look, but also it's just so you have heard these things in this lecture. Convolutional neural networks, or CNNs, are visual networks. They're really good at looking at things, and basically the self-driving cars are using CNNs inside to make sense of what the camera is showing them. Then you have GANs, or generative adversarial networks. I mentioned them before. They're really good at translating one thing into another, and like, it's very general, but these networks are very general. And you have recurrent networks. These networks are very good in time series. So they're used for seismic data or for well log interpretation and interpolation. And then this is on the bleeding edge right now, but welcome from the future. It's probably old and a really old hat for you. Neural architecture search, or AutoML, is the way to actually find this combination of neurons and weights and whatever you need automatically and build a model for you without any thought. So kind of scary for me as someone that is just studying this, because essentially it's automating me away. Transformer networks are used for translations mostly at the time. So if you have an input sentence in English and want an output sentence in German, then you usually use a transformer network. But this space is moving so fast. I mean, convolutional neural networks kind of sparked the nascence of deep learning and, well, of the recent boom about AI and all that. GANs have just been invented not even 5 years ago. So when you watch this, there's once again going to be many more, and you can come up with your own. I'm going to show you later with something that I came up with. So concluding, what is machine learning? For me, it's a different approach to a problem and a bit of a different way to think. Let's have a look at a concrete example. So when we have seismic data, you've probably seen this before. This is the F3 data from the Dutch offshore, and you want to do your inversion, you invert, you have some kind of velocity there, and then you make your forward model, and in this infinite loop, almost infinite loop, you invert your seismic using the wave equation and just, yeah, well, you know FWI, right? In machine learning, we're using this as our input, the seismic, and we're using our answers, the velocities, and we're plugging the entire thing into our machine learning model, which is a black box. So this is one of the big criticisms that I always hear. But let's have a look at the meaning of the word black box, because it actually means a little bit different thing than what people usually take it for. Originally, it means black box is unaware of physics or unaware of the model. So it's essentially a thing that you have that is modelless or doesn't use any of the information that you assume. So that's kind of what I like about it. It helps you build relationships without assumptions. Let's take a step back, and like everyone is always telling you, it's really easy to build machine learning models. I want to have a bit of a toy example, which is the MNIST. These are handwritten digits. And well, a little bit of live coding. First, we import TensorFlow, which is my choice. There's also PyTorch, which is an excellent choice. And then we're importing our MNIST dataset, which comes with the TensorFlow distribution. On the side, you can see how I execute the code live. Then now we're actually loading the data, and we have to split it into our training data and our test data, which is a concept from statistics. You always want to have some data where you actually have labels to see how well you're actually doing on data the model, the learning model, has never seen. You can see it there. It's X-train for the input data and Y-train for the labels, and our X-test for the input test data and Y-test for the labels for the test. Then we do a bit of data conditioning to make the learning easier. And every machine learning engineer will basically tell you that this is kind of what you spend most of the time at. Data munging and making your data ingestible. And then the training is really easy. We're building a sequential model. First, we're going to flatten the entire image. So remember, it's a handwritten digit. It's 28 by 28 pixels, and we're just making a long string out of it. You can see this here, and then we're going to put that into a dense layer, which is just the same as you've seen before. So neurons, and we're going to take let's take 128, and then we're going to apply a non-linear function to it, which is called ReLU in this case, with an U. And then we're going to put dropout on it, which is one form to regularize our network. So in essence, it's forgetting some of the neurons, so it's harder to remember. And then we're putting it into a dense output, which is 10. So all the numbers from 0 to 9. And the activation function here, softmax, is just for classification. We need to compile our model. We have the loss function, and we're going to define our optimizer, which is Adam. Perfect choice for the beginning. The loss function is categorical cross entropy, which is very good for classification. And then we also define our metric, which we're just going to take accuracy because it's very easy to look at. But in geoscience, it's often not a good choice, just a basic choice to have a look if it's going okay, right? Now this is the machine learning part. Model.fit. Put in your X-train, put in your Y-train, execute the code. You can see it running here, and like 3 epochs should be enough to get a decent model. You can see how the loss is going down and the accuracy is going up. And yeah, it's kind of magic. This is machine learning. And in the end, we can evaluate on the test set, and we see that on unseen data, our model is performing extremely well at 97%. So out of 100, it is getting less than 3 wrong. And I mean, if you have any doctors in that set, I would definitely get more than 3 wrong. Let's have a look at the explanation, because everyone is always saying black box, you can't look into it. Well, I beg to differ. We can calculate Shapley values, they're called, and there's going to be much more when you see this video, because essentially this is a really, really booming topic of research. So our number 2 at 0, 1, 2, we see a lot of red values, which basically tell us, oh, this is a positive influence, why this is interpreted as a 2. And the 1 You see it at position 41, that it's evaluating the straight line a lot as positive and the free space around it as well as positive. 0, we go to location 0, where you have the free space in the middle as positive, and only the circles on the side are positive. The rest is sometimes even negative. And if you go to the position of 6, you're going to see why. If you, this 0 has a little piece on the top that might make it a 6. And the 6 is actually negatively impacted only by the circle on the side. So you can interpret your models like this. And like the 4 here is my favorite one, because if you go to the 9, you can see that it's just not a 9 because it doesn't have a line on the top. So if it had a line on the top, this would probably be classified as a 9. So model explainability is an active field of research, and this is 2019, so when you're watching this, there's going to be more. But these keywords will probably send you off in a good direction. So for convolutional networks, attention, deconvolution, and adversarial attacks are good things to start. Adversarial attacks are really fascinating because you can basically try to mess up your neural network by adding noise into your network. And sometimes 1 pixel is enough to throw off your entire network. 1 sticker is enough to throw off your entire network. Like, there's fascinating stuff out there. LIME, local interpretable, model agnostic explanations, is really good if you take a well and pass it into your network or into your random forest. Then your well basically gets explained, gets visualized, and you can make sense why you're getting this kind of netto growth out of it. The Shapley values that we just looked at, it's clear that when you know what's positively or negatively impacting the decision to classify your number into a certain bin, you will be able to make much more sense of what the network actually sees. But the most important thing probably is simple models are easier to explain. So these neural networks that we're building, and I'm going to show you in a second, are huge. There's so many parameters in there, even for smaller networks, and we didn't build a big network before. So most people tend to go to random forests. Random forests are smaller models that are easier to explain. Support vector machines are smaller, simpler models that are easier to explain. But the problem with that is deep learning is so powerful and so good at doing these complex tasks because those are complex models. So you have a trade-off here, and you have a decision to make if you can use a simple model or if you have to upgrade to a more complex, deeper model. Back to the code, we can just visualize the different layers of our code, just say model.summary, and then on the side we see our flattened layer, our dense layer here, and well, if you go all the way to the bottom there, you can see that this simple model has 100,000 parameters that get adjusted. You saw how fast it is, which is amazing, but it's a very complex model for a task that isn't that complex. But you saw a payoff. 97% is not a joke. How is this a different way to think, you might ask? And I think you have to be aware of what you're putting into your network, into your machine learning model. So machine learning will learn anything. There's a really cool example where they're teaching like a little robot spider to walk. And at some point, they're wondering, okay, what happens? How does the spider change? If we're telling it, please, it would be nice if you used as few steps as possible. They let it learn just overnight, they come back, and the model is saying 0. It takes 0 steps, and they're mind-boggled. And the spider just flipped on its back and uses the joints to crawl to the goal. So it will learn anything, and you have to think about what you're asking it to do. Think about your system. Geologists will love this. You have to think about your whole system, what's happening, how it is growing, what is really going on. So like implicit bias is very important to think of in that sense. Is your data skewed? I mean, most well data that we have is on prospects. We don't drill randomly. So our data is biased to places where we at least expect a certain geology. So if you only take your well data that has oil shows in there, you're actually cheating by so much. I mean, think about it. Oil is so seldom that we have an entire industry around it. So if you're teaching your machine learning model that all my wells have at least hydrocarbon shows, then you're gonna get an answer that is probably very similar, that it is finding hydrocarbon. But you might want to consider sprinkling in some wells that were a loss. You also have to think about the old correlation versus causation thing. So machine learning is basically a big correlator. That doesn't mean it's not useful, but you have to be extremely careful to take causation from it. And you might want to probably consult a statistician for that. Your statistician is going to be able to set up a system for you to test if this is actually causality or just correlation. So black box stands for unaware of physics, but since we're talking about our explainability, maybe we can gray box it and make it somewhat aware of physics. So when we think about our systems, let's have a look at a cool YouTube video. Like, I love this stuff. The arm on the bottom is basically learning to throw arbitrary objects into boxes. It does not know where the boxes are. It only sees the objects, but it knows if it hit the box. So it's a yes or no. And we are using residual physics in this network, which is added on the bottom left there, to make it better. And the numbers behind this are very clear. If you're only using the networks, you get 33% accuracy. That means 1 in 3 of your throws makes it to the correct box. If you're only using physics, and this is fancy physics like partial differential equations and such, you're getting up to 2/3. So 2 in 3 will make it to the correct box. Now, if you're using the simple physics and calculating residual physics with a machine learning model, you're getting up to 84%, which is better than 4 in 5. You're missing 1 of 5 throws or less. So this is really the selling point I see in adding domain knowledge, in adding physical knowledge into your network architecture, into your system. Coincidentally, this is something that I also learned and also developed like parallel to the tossing bot. I'm including some very simple physics, which is the AVO, the angle versus offset, in my network architecture. And I just presented it at this EAGE conference yesterday. So you can have a look. Down there's the link. You can download it for free and have a look at the presentation and what we've done there. There's a bonus, and we're almost done here, because something that I see that should happen will happen soon. And I mean, if you're watching this far enough in the future, this will be an old hat for you. Right now, we're taking our input seismic, and we have a fault network to interpret faults. We have a horizon network to interpret horizons. You see how it's going. What if we build a multitasking network that can then plug into our faults, plug into our horizons, and go towards system understanding instead of just building one model, because in the end, one model really isn't enough. And if you capture these different things, at least right now as they do in natural language processing, you get much more powerful models, and you're actually harnessing what deep learning is made for, with capturing very complex systems and giving you understanding of it. So at this point, it just leaves me to thank you for making it all the way through. I hope you're taking home something from it. If you want to look at more deep learning stuff, I have a YouTube channel and my blog. And if you want to have more geoscience content, then have a look at the other student e-lectures and the other e-lectures on the EAGE channel. Cheers.